Okay, I guess that we can start slowly. You know, uh, so last time I'm recalling quickly here, like we have shown that it's a very, very important result that, if U is dominated, okay, let me just highlight now. So the theorem last time, again, this is theoretically very important and also that in various scenarios, it plays an essential role that we have if U is dominated by L plus C, and if gamma is a ULC calibrated curve, then we imply that U is differentiable along the calibrated curve except the two endpoints, and at the point of differentiability, we have, the formula of the gradient that can be written in terms of dv of the Lagrangian, okay? And we are in the fixed energy level. And also it's important to emphasize that you might not be differential at the endpoints. And this is truly, happening. We're gonna come into some examples, either explicit or implicit, so that you can see this kind of situation. Still, so far I haven't proven to you. Maybe let me recall quickly the Weekend Theorem that I haven't proven to you what's going to be sort of the case that whether do we have the existence of a function. So the Weekend Theorem says that there exists, after that we have done a lot of works, the Weekend Theorem can be stated in an equivalent way like this. So there exists a Lipschitz function U, okay, here you can say U is in Lipschitz of the torus such that U is dominated by L plus C naught. Okay, C naught is the critical constant, right? Or equivalently, h of x dux is less than or equal to C naught almost everywhere. And so the first one, we already proved the existence of such a function U. The second point that is important, and we haven't so far proved it yet, is that and for h x in the torus, we can find a calibrated curve, gamma mapping from minus infinity 0 to the torus with gamma 0 equals to x. Okay. So again, I kept drawing this picture again and again. What is really important is that we are able to find a calibrated curve going from minus infinity to 0, ending at 0, which is x is gamma 0. And we have shown that, U is differentiable along this characteristic, but clearly that it might be the case that U is not differentiable at the endpoint gamma 0 equals to x. Okay, so that is a very interesting phenomenon, right? Because you have a point, that point is the ending point of your right. Your function is differentiable everywhere along your right, but not at that point. And that is, again, the main content of the so-called Weekend Theorem. Again, this is, I call it the Weekend Theorem because in terms of dynamical system, the Weekend Theorem was done by Fatih by, I'm going to introduce to you the methods, and we're going to build it step by step, and eventually it boils down to a fixed point result. I guess I can present to you more than one proof. We see about that. And so this is Fatih, this is presented in his book, in the book. But it turns out that earlier there was already a PD proof. So in the PD language, It came from a surprising result earlier in the 80s. Maybe this is around 2000. I don't know, precisely when. But in the PD language, it was done by Lyon's Papanicolaou Varadan in an unpublished papers around 1987. Okay. And surprisingly, PD was for homogenization theory, and it was different from the dynamical system context. And eventually, people realized that the two are essentially the same. Okay, so that's our goal. We're gonna go start proving the Weekend Theorem, and to do so, we need to do some preparation steps. Prep steps, and today one of those prep steps gonna be minimal actions with fixed time. Okay, for fixed time. Because actually proving the result that you have a backward characteristic forever for all time is not something very easy. And normally we would have to start with something for fixed time and try to, obtain the results that sort of hold for all possible time. Okay. And so that's exactly what I'm highlighting now on the left panel. We're gonna deal with minimal action for a given time. And in your mind, you can think of this one like nearly a metric distance, nearly. I mean, not quite, because, for example, we don't have symmetry and stuff like that in general. But what we are defining is that you're given a fixed time t, and you're defining a function ht of xy. Essentially, it's the cost taking, from going from x to y in a given amount of time t. Okay, so what we are doing is that you are trying to find what is the minimal cost. Right, so this is the minimum cost of going from x to y in a fixed amount of time, say t greater than 0, that is given to you. So you can choose as many admissible curves as you wish. I mean, essentially, this is already like, like the earlier minimizing action functional, right? We are just defining it, that for two given points, we can define a function, and we are going to deal with that functions that, we're going to be able to vary the endpoints. But, each of the function itself, is exactly a minimizing problem, right? So you have a curve gamma with gamma 0 equals to x, gamma t equals to y, and you are trying to minimize the action functional. And this is again our object for the first 10 lectures. No, nothing new here, right? What is only new here is that we are going to allow our endpoints x and y to be varied, and we're going to try not to study about minimizers this time. We're going to try to study about the dependence of h on x and y. Okay, so maybe let me make a remark. That's exactly what I just said. Ht xy is not a new object. Okay, what is new here is that we try to study the dependence of ht on x and y more systematically. Okay, right? Because earlier we didn't say anything about varying the endpoints. What's going to happen? Earlier we were just saying, okay, fix the two endpoints. I'm looking at this exactly minimizing problem. And also in calculus of variations, most of the times you are given a fixed boundary data, and you try to minimize your functions with respect to that admissible class. Okay, yeah, but now we vary the data. Okay, and roughly speaking, you can think of think of ht of xy as some sort of, again, this is not a really metric, but some sort of distance from x to y. Okay, again, under additional assumptions, you might have that is a metric, but in general, it's not. Okay, for example, it's not positive, it's not equal to 0 when if and only if x equal to y is not symmetric, but we see about that. Okay, so let me state the properties. Most of the properties are not new, and some are straightforward. So let me try to highlight which one are straightforward. Let's see. So the first one is straightforward. HT is bounded from below. This is straightforward because h of the L is bounded from below by its minimum value. I'll write down very quickly. The last one is also not new. The last one, it was about already a problem in calculus of variations that we have dealt with in the first 10 lectures, right? We have proved that there's a unique minima. No, I take it back. There's a minimizer, and if we have additional assumptions that L is nice, is CK, and locally uniformly convex, and that minimizer turns out to be satisfying the Euler-Lagrange equation, and hence is unique. But in general, that we have discussed, if L is not nice or if it's not locally uniformly convex, then you can have more than one minimizer. Okay. Yeah, so I did say it out loud, but the proposition is that 1 and 4 was already done earlier, or we can say by this moment now is standard. It's not standard at all for the last result, but again, after quite a few lectures on that, it's standard. And the first bound is also obvious because you take infimum over the action functional L of gamma dot ds. H of the L inside here is going to be greater than the infimum, right? LXV, or minimum. So you're going to just take that, minimum value, and take the length of the integral to be t, and that's it. Okay? So I'm just using the fact that the Lagrangian here is always greater than equals to this is minimum value. Okay. What else? The third point is also not too hard to show. Okay. So what is really new in this proposition, in this result, is the second one. Okay, the second property is new. So this is new. This second property is new, and in optimal control, it's called dynamic programming principle. Or DPP for short. Okay. But in general, if we have you haven't seen that, it's not a problem. We're going to prove it clearly, and what is quite nice is the following interpretations. What we say is that, yeah, I mean, to go from x to y in a fixed amount of time t plus t prime, what you need to do first is to go from x to some z for an amount of time t, okay? And then from z, you try to go to y in an amount of time t prime. And because going from x to y is optimal, so what we are talking about here is that we need to choose an intermediate point, intermediate stop that is optimal. So what we are saying is that we need to take the infimum among all of the z, so that that stopping point or that sort of point in the between is being chosen optimally. And that's essentially the so-called dynamic programming principle. Okay. Any questions or concern for me up to this point? Again, please do speak up if you have concerns or questions or anything. Um, again, I'm trying to be a quite basic and fundamental all the time. So if it's kind of obvious or something that is being repeated or something that is, I mean, you want to sort of like skip it or you want to, make it clearer or something, then do let me know. Okay. Um, So this is what I said here. The part 3 is easy, right? 1 and 4 was done earlier, and 3 is kind of easy because we didn't do it exactly for h of t, but what we have done is that if you take any curve gamma which is admissible, right? Then you have, because um, U is bounded, dominated by L plus C. So you see that U evaluated at the two endpoints is being less than equals to the action functional of L plus C acting on gamma, right? And now you're taking infimum over all such admissible curves gamma, and that allows you to get the conclusion that you know U is bounded from above by this one. And by the way, um, this one, although it looks very simple, but this is sort of like this is kind of also has an analog in optimal transport. In a fancy way, ht of xy here can be thought of a minimum cost minimum cost of transporting a measure, in this case a delta direct measure delta x, to another measures delta y in a given time t greater than 0. Okay, so although it looks very simple that you try to go from one point to the other, another way to interpret this one is essentially a cost function in optimal transport, and the result in the box here is some sort of like relaxing or duality principle, whatever you call it. In general, you can try to define a function ht mapping from a measure mu to a measure nu, for mu and nu are given probability measure, for example, and that would be exactly an idea in optimal transport. So although it looks very simple, but it already has some remarkable analogs. And of course, interpreting this and doing this is not easy. For example, interpreting this correctly for the viscous case, if you have the viscosity term, second order equations, it was only done recently, for example, by Diego Gomez, Hiroyoshi Mitake, and I. So, still a lot of things that we didn't understand. Anyway, um, so yeah, um, yeah, it would be better if we understand it more, but not that clear at this moment. Okay, so now let's try to prove 2, which is exactly so 2 is clearly a new point, and it's a really important point, that to go from x to y in an amount of time t plus t prime, then what you need to do is that surely you need to stop at some point after t, right? So you go from x to z after time t, and then from z you go to y after time t prime, and we claim that, we have that this is equals to the minimum over z in the torus. Okay, did I say minimum, infimum, or minimum? It doesn't matter. Okay, let's do infimum for now. Later on you see that it's exactly the minimum, but for now we haven't proved anything about the continuity of ht, so let's say infimum. Okay, so that's an important result that we are proving now. All right. It turns out that proving this one is not too hard, in a way, as often the case for the infimum or supremum proof goes, you just need to check it carefully, right? So the first thing to check it is that you say, well, okay, fine. I know that I need to go from x to y, in an amount of time t plus t prime. So this is my curve gamma. I have x is gamma 0, y is gamma t plus t prime, right? So that's fine. So I know clearly it's gamma t at some point here is this, no matter what, I have to go through gamma t. So, I'm just breaking the integral on the left into two integrals, right? From 0 to t and then t to t prime, okay? As simple as it is, right? And I noticed that, well, the first integral is greater than equals to the cost functions going from x to gamma t, right? Because, the cost function going from x to gamma t is defined to be infimum, and this is one representative, so it should be, greater than equals to ht of x to gamma t. And the second integral is greater than equals to ht prime of gamma t to y, okay, as typically as it goes. And gamma t here is just one typical value, right, for some gamma t. So clearly that is going to be greater than equals to infimum over z of the sum of the two, right? Because the two here over all possible z. So, it's really going to be taking the infimum is going to be less than the value of some typical gamma t. Okay, so that's it for the first part. Um, so we got already that by the first part here is that the left hand side is greater than equals to the right hand side, right? Because I can take infimum over all possible value to get that. So the left hand side is greater equals to the right hand side. Now we need to show. So next we need to show that right hand side is greater than equals to the left hand side, right? So how do we do that? Well, I mean, to prove that right hand side is greater than equals to left hand side, we would need to take any possible z, right? So what we are doing is that, okay, so I'm gonna write out, okay, this is x, this is y. Yeah, we pick any possible z in the between, not in the between, any z in the space, okay? And you say, hey, I'm gonna choose a curve alpha that connecting x to z, and a curve beta, different color is better. A curve beta is connecting z to y, and that's exactly what I'm writing here on the left panel. We are selecting alpha connecting x to z after a time t, and beta connecting z to y after an amount of time t prime, and then you gonna try to combine the two curves to create a new one, right? It's just a natural idea. Again, the point is that our curve needs not to be smooth, right? It can be piecewise C1, or it can be absolutely continuous, doesn't matter. So you just define naturally gamma to be the combination of the two curves, and then you see that gamma is admissible, right? So when gamma is admissible, then you imply right away that the first box here, right? The first box that I'm putting on the left panel is just that, ht plus t prime xy is less than equals to that specific integral, because gamma is an admissible curve. And by the definitions, we split it into two pieces. The first piece is just the integral on gamma on alpha. The second piece is the integral on beta. And because alpha and beta are being selected independently, they are not depending on each other. So you can just take infimum over alpha and infimum over beta independently, right? Again, z is a point that is already given to us. Um, okay, so you take infimum over alpha and beta, you get that, you know, uh, so take infimum over all possible alpha and beta, we get ht plus t prime x2y is less than equals to ht of xz plus ht of zy. And then because z is chosen arbitrarily, we take infimum over z to get the conclusion, right? Okay, so that's it. It's really simple. It's not something like, I don't know how to put it. It's not something crazy. It's really fundamental, step by step. Yeah. Okay. Any question or concern for me at this moment? Yeah, I guess today lecture is quite a breeze for you guys. Just going smoothly, and I don't know. So this first result is not a big deal, but it turns out that typically, yeah. So maybe let me make a remark. So a remark here is that the so-called, which is proof, is so-called dynamic programming principle. Programming principle is not too hard to prove, but typically plays quite an important role for uh, for verifying that is a you that the function, I'm being vague here, but the function is a solution to a PDE, or to use in numerics. Okay. For example, there are certain methods called fast matching methods, or some other methods in numerics that they use. This sort of like hidden properties of dynamic programming principle very smartly. Okay. So it helps you to go step by step, scanning in a smart way to do fast matching, or whatever that you can do. Study the front propagation problem in a very quick way in numerics. Okay. Now, what we're gonna prove next is the first one is easy. Today, what is the most important one is this lemma. Okay. So yeah, maybe let me just analyze it a little bit. There's one claim that it looks very simple, but it turns out to be of very important nature that we're gonna need to use it later on. Okay. So first, we're gonna obtain here. So we analyze more about ht of x and y. We first obtain an obvious upper bound of ht. Okay, and it turns out that this upper bound is how should I put it, is is kind of trivial in a way, but it also tells us a little bit more about the nature of the problem, right? So again, let me just write out the upper bound, and then I will give you one of the reasons why that this is not a good upper bound. So you just choose to connect x and y by a line segment, right? Whatever you choose. In this case, what I'm writing down here is that, okay, so I need to go from x to y, right? In a time t. So if you go in a line segment, then your velocity should be y minus x over t, right? That's exactly what is written here, right? Because you are going in a constant speed in a line segment. I should have said that constant speed, but okay. So the velocity is y minus x over t, and you can just write out then your ht function, right? So you have ht is dominated from above by this integral. This integral can be written explicitly as just this integral, right? So maybe let me write down here. So I have ht xy less than equals to integral from 0 to t L of x plus s y minus x over t y minus x over t ds. Okay. The first term is not a big deal. So this one is always in the torus, or you can also think of it as in Rn with periodic coefficients. So whatever the positions are, they are in a compact set. Okay. What is worrisome is here, right? The velocity is kind of like blowing up if time is getting to zero, right? So you know so we have to be careful when time goes to zero, and that's exactly the point, right? You see that I can write down easily an upper bound for ht. So ht is bounded by t times the maximum value here. So this maximum value is fine. Again, accept the fact that I'm not too happy with v bounded by x minus y over t. Okay. Or you can say that, because the distance between x and y is at most root of n, because we are in the torus. So you can change it to, max of lxv for v less than root of n over t. Okay. So you have t here multiply with root of n over t, but we should note that L is superlinear in V, right? So if V grows like 1 over t, then t times L of xv gonna tends to infinity as t goes to 0, right? Right, because you see that t only grows linearly, but L of xv grows faster, right? It grows super linearly in V. So you can see that this one can be written as okay. Let's say that you can write this as L of xv over V, right? Because t is like 1 over V. And you see that this one goes to infinity. So what it says here is that ht is not too nice if t goes to 0. Okay. So clearly this tells us that so if x is not equals to y, then ht of xy goes to infinity as t goes to 0. Okay? So it's blowing up actually. So we have to be careful. That's what I'm saying. And in fact, uh, this is not too important. We are not using it, but an important remark here is that, um, so fixed x in the torus, the map y to ht of xy can be thought of as as a fundamental solution to the equation, to the PDE that I have, say phi t of phi t plus h of x d phi equal to 0 in Tn cross 0 infinity, and the at the origin, at the beginning, I have phi t of x0 equals no, so change it to y, equals to plus infinity if y is not x, okay, and equals to 0 if y equals to x. So it's kind of a fundamental solution to this PD, so then we would have that phi of yt gonna equals to ht of xy actually. But again, I mean, we are not gonna use this, but in general, this can be thought of as really a fundamental solutions that you solve the equation with initial data to be kind of weird, right? 0 plus infinity, and then you goes as time goes, and ht of xy can be really thought of as this fundamental solution. Okay, but again, it's not our goals. So what is really worrisome is that you see that I highlighted it here. We just prove it that if t is greater than 0, then ht of xy is bounded by ct. However, ct can blow up as t goes to 0. So the next part, this is a new result, and this is a very important result that we're gonna keep using later on to prove the Weekend theorem that I put a red box here. That if you fix a time sigma greater than 0, then for any time t greater than equals to sigma, so we need a lower bound for the time, which is sigma, you can find a constant k sigma only depending on sigma. That is for any time t bigger than sigma. T can goes to infinity, whatever, it doesn't matter. Just need to be at least sigma. Then you can find that for your minimizer to your function ht, your velocity of the curve is always bounded by k sigma. Okay. This wouldn't hold um, if you let sigma goes to 0, right? Because to go from x to y in a small amount of time, then your velocity needs to be really big. But if you allowed you to have certain sigma, then for any time t bigger than sigma, you can have this bound. And again, this is remarkable and it's very important. Um, okay.
Can I ask a question about the HT bound?
Mhm.
Um, so in that second, so that inequality in the middle term,
Mhm.
uh, it seems like the x, so that there's x in Tn,
Mhm.
and then there's v is less than or equal to x minus y. It seems that x minus y, the second x should be the x from the left hand side, right? And then the
Yes,
first
yes.
x is just arbitrary x.
Oh yeah, yeah, right, right, right. You're absolutely right. I mean, I'm okay. Yes, absolutely. Let me change it so that it's less confusing. Um, yes, this would be z of v and z in the torus. Yes, so that's probably less confusing.
I see. Thank you.
Yeah, thanks. So again, uh, you know, absolutely, it's just that saying that, okay, and here that what I'm saying is just that because we are dealing with the torus, with the compact torus, so or compact manifold. So in terms of the position, I'm good. I'm not worried about whether I'm traveling to infinity or not. But this is also saying that for non-compact manifold or for Rn, developing Weekend theory for this one is hard because you have to face the problem of things traveling to infinity. Do you put assumptions there so that everything is nicely controlled. And as I said, so far, I am aware of some results that develop weekend theory for either non-compact manifold or Rn, but those are not satisfying to my views, because for those you would need to put assumptions in such a way that the sets that you care about are compact. So you don't really allow things to go to infinity, or maybe those are the correct setting. Without those, you wouldn't be able to do that. Okay, so thanks a lot for the comment, and I agree that it was a little bit confusing. Okay. Um, all right, so now I don't have to worry about the fact that HT is bounded by CT anymore. Maybe I'm just gonna emphasize that. Um, I'm just gonna emphasize that. Note that CT or CT tilde converges to plus infinity as t goes to 0. Okay, that's the only thing I would like to comment. Okay, now let's prove the last piece of the puzzle for today. And as you see, it's quite simple. Why is it simple? Well, we are using the fact that our curve is already nice, CK and stuff like that, right? So to see the second part, I'm using that um, mm, what? Uh, yeah, I'm just I haven't put it to the constant c sigma first. So I'm just gonna write out, okay, I have this bound, right? So you have this bound, and then you are using the fact that again, gamma is ck, right? So gamma is ck is a minimizer, right? So you can you don't have to worry about the regularity now, right? So you can just find a point t naught in the between, so that the Lagrangian is less than equals to the maximum value here, which is c tilde of t, right? Or you can just call ct, I guess. Why did I change it to c tilde? Oh yeah, c tilde is because I don't multiply with t, okay? Uh, so that's that, and clearly that you see that if, let me say it, if here, so here, for t greater than sigma, then clearly c tilde of t is gonna be less than equals to c sigma, c tilde of sigma, right? Because the bigger the t, the smaller the region for v is. So that's why what we need is really that t is bounded from below by sigma. So we get that the Lagrangian on gamma gamma dot at t naught is less than equals to c tilde of sigma, right? And remember that and so note that here that L is superlinear, right? So it's superlinear in V, and it's bounded. That means that V is bounded, right? So you imply that V, which is the velocity, is bounded. Okay, so um, gamma dot of T naught, which is a velocity at a point, is bounded by some K sigma. Very simple. Um, if we stop here without using some of the tools we have developed, and we are not done, but luckily, again, we have developed so much so far after 2019 lectures that we have enough things to do now, that we don't have to reprove everything, right? It's enough to prove that if the velocity is bounded as at a point, then it's bounded everywhere. So this is a very remarkable thing. So it's a remark. If gamma dot is bounded at a point, one point, then you imply that gamma dot is bounded everywhere. Okay, so that is a very remarkable thing. And why? Well, I mean, thanks to the tools we have developed so far, gamma dot is bounded, meaning that the generalized momentum P is dV of L gamma dot is bounded, right? Again, by changing K sigma to some other constant K sigma, I can just keep that the same. So the thing is that gamma dot T naught is bounded implies that P of T naught is bounded. Okay, and T naught is bounded implies that our energy level is bounded, right? Because we have that H of XS PS equals to H of XT naught PT naught is bounded, right? Because we are on the same energy level, and because PT naught is bounded by a constant depending on only sigma, then you have that our energy level is bounded, and because our energy level is bounded, we imply that PS is bounded by a constant K sigma, and P is the generalized momentum. From here, you go back from P to gamma, right? So we are doing it all the times that we switch from velocity to momentum, momentum to conservation of energy. To get momentum is bounded, and then from momentum is bounded, get back to velocity is bounded. Okay, so it's a great way to be flexible. That's what I meant. That it's always important to be able to switch around and use all the tools that we have had. Okay, so I'm done for today's lecture. It's simple as I put it. We have developed certain elementary but basic properties of H of T. And one of the most important thing that we have done today is that if the time is greater than equals to any given fixed constant sigma, then sigma greater than 0, then we can say that, your minimizing curves, gamma gonna have bounded velocity, and this bounded uh, velocity is only dependent on sigma. It doesn't depend on any t. So in principle, you can let your time goes to infinity. It doesn't matter. Okay, and that's it for today. Do we have questions or discussions? Anything of your concern or anything that is not clear? This K sigma is very important as we go later on when we try to do certain fixed point theorem, because what it tells us is that we have a uniform bound for all possible minimizers gamma, right? And once you have uniform bounds, you can use certain compactness results, whatever that means. But getting some bounds independent of the curves, independent of the minimizers, is quite important. Okay, although the proof is not too complex, but without the tools that we have developed from the beginning, it wouldn't be too easy. Okay, all right, then I guess that we can stop today now, and as always, again, do feel free to bring up the questions or concerns to me. And my goal, as always, that you put some time for pre-lectures, and you stay here for the class. You think a little bit more about that as as time goes, or as you need it, or later on maybe that you're going to need to use it in one way or the other. That's enough, because this is by the end a topic course that I want to bring to you certain modern techniques that people have been using in Hamiltonian dynamics and in PDE. All right, so thanks all, and yeah, we have one more lectures to finish half of the semester, right? So far so good. So I'll try to finish up and then post the next lecture notes in a timely manner. It takes some time, but I'll get there. Okay. So thank you all, and then I'll see you on Friday. Bye for now.